Hello, everybody. I should say good morning to some of you and good afternoon to others. My name's Alasdair Beal. I'm a civil and structural engineer based in Leeds, Yorkshire, in Great Britain. Over the years, I've written many papers on various aspects of engineering, but not on relativity theory. This is a bit of a venture off to the side. What happened was like many people, I was intrigued by the twins paradox and never could quite understand it. I'd read several explanations that were all different, but they all claimed to be consistent with Einstein's theory. And I have a principle in these situations. If you're getting these mixed messages, go back to the original. Firstly, because that's where it all started. And often the original is better than the explanations brought out by people who are trying to improve upon it. And so it was that I got a copy of Einstein's 1905 paper and started trying to understand it. As you'll see in the course of this lecture, I ended up in rather a different place, and as a consequence ended up writing the paper that's published this month in Physics Essays. Before going into my talk, I'll mention three people that I'm very grateful for the help of over the years on this subject. One is Gertrude Walton in Winchester in Britain. She was the first person I came across who was a critic of special relativity, but clearly not a crank. And her angle on it was that there were problems with Einstein's mathematics. The second person is John H. Field, who was a researcher at CERN in Geneva. He's now retired. He's written several papers on the subject, and when I was working my way through this, trying to make sense of it, he was very generous with his time, commenting on previous drafts or ideas that I was throwing around. And finally, Radwan El-Kassir in Beirut in Lebanon. He's also an engineer, interestingly, but he's written several papers on the subject and a book. And he's come at it from a rather different angle from me, but we've come to broadly very similar conclusions. As he puts it, any rational, no matter what way you come at it, if you've done a rational analysis, you come to the conclusion that Einstein's calculations are wrong. So I'll now share the screen and go into the talk. Okay, so I ended up, it wasn't what I first intended, but I ended up writing this paper of my findings on Einstein's calculations, and it's been published this month in Physics Essays. To give you an idea of how I'm approaching it, going back to absolute basics, what should a scientific theory do? It should, firstly, be logically and mathematically coherent and consistent. Secondly, it should fit the known empirical evidence. And thirdly, ideally, it should make testable predictions. Now, I've put those three up deliberately in that order because the first one, if the theory fails the first test, there is no point in going on and looking at the second and third tests of it. So what I'm looking at is the logic and mathematical coherence of Einstein's theory as he set it out. His paper on special relativity was published in German in 1905. The first English translation was actually published in Calcutta. It was by Sahan Bose and published in 1920. And the most common translation that people have was by Perrott and Jeffrey in Britain in 1923. Now, that one has been reprinted many, many times. And in fact, there was a new edition of Einstein's papers edited by Stephen Hawking, published in the USA in 2007, and then published in a different title in 2008 in Britain. And those are on special relativity, they still show the Perrott and Jeffrey translation. So it's been in print for over 100 years. That's the text that I'm using as my reference. I should say I'm only looking at the kinematical, what he calls the kinematical part of his paper, and simply I've looked at Einstein's mathematics and logic in their own terms as he set them out there. A couple of apologies in advance for people who may be disappointed with some of what I have to say. I've got no esoteric physics to offer and no fancy mathematics, just some simple algebra. And for ease of reference, of cross-reference, I've used the same notation as is in the Perrott and Jeffrey translation in these books, so that if I put up an equation, I said this is one of Einstein's equations, anyone that doubts that is free to look at Einstein's paper in one of those books, and they can check for themselves whether I've represented it fairly. So, why focus exclusively on the 1905 paper? Well, partly it's for historical interest. This is where it's the paper that started the whole business going. But also, despite the time it's passed, it's still regarded as an important paper in the present day. Here's what Stephen Hawking has to say about it in the introduction to his 2008 edition of the papers. The details of Einstein's reasoning and the simple algebra behind it are explained nowhere better than is found here in Einstein's own words. It's quite an endorsement. So, what was the background to Einstein's paper? Well, in the 19th century, theories of how light travelled through space and so on, ether theory was dominant. But in 1887, the Michelson-Morley experiment threw up quite serious difficulties for ether theory. In the years that followed, Lorentz and others derived transformation equations from ether theory, which were regarded as useful. But on the other side, relativity theory was gaining ground among physicists. I think if you ask what was Einstein's stroke of genius in 1905, I think his stroke of genius was to see that if he could unify the Lorentz equations, the principle of relativity, and the principle of the constancy of the speed of light in one theory, he could be onto a winner. So what are the assumptions of the special theory of relativity? This is as he set it out in 1905. The first is the principle of relativity. The laws by which the states of physical systems undergo change are not affected whether these changes of state be referred to one or other of two systems of coordinates in uniform translatory motion. The second principle is the principle of the constancy of the velocity of light. Any ray of light moves in the stationary system of coordinates with determined velocity c, whether the ray is emitted by a stationary or by a moving body. He claims that purely from those two principles, he was able to... I'll just take this little bit off the bottom of the screen. That's better. He claims that he could deduce the Lorentz equations purely from those, and therefore there was no need for the ether, or as he puts it here, the view to developed here will not require an absolutely stationary space provided with special properties. Before I leave this slide, you look at it, and I look at that and say, hang on a minute, if there's no absolutely stationary space with special properties, what is this reference to the stationary system of coordinates that light moves at velocity c in? To understand that, you have to consider Einstein's definition of the stationary system. A stationary system is a system of coordinates in which the equations of Newtonian mechanics hold good. That's effectively any uniform translatory motion. In other words, if it's travelling in a straight line without accelerations in any direction applied to it. In order to render our presentation more precise and to distinguish the system of coordinates verbally from others that should be introduced hereafter, we call it the stationary system. I think this is a very unfortunate approach he's taken here, because in fact, in the paper that follows, all of the systems of coordinates he looks at are in uniform translatory motion. Therefore, any of them could be regarded as the stationary system. And of course, also, what he's calling the stationary system isn't stationary in the normal sense of the word. So it's a very unfortunate choice of words. It causes quite a lot of confusion. But if I'm not looking at his paper, we're stuck with it. So I'd ask you simply, anytime the word stationary comes up, remember that in Einstein's definition, it doesn't mean stationary in the normal sense of the word. It means it's in uniform translatory motion. And in essence, it's what he's choosing as his reference system for a particular piece of analysis. We move on. A lot of his calculations are based on a system of synchronizing clocks at different places in space by use of light flashes. Now, the technique, if you imagine you have an observer has a clock and there's a clock somewhere else in space, how do you synchronize the two of them? This is the method that Einstein discusses. So, a ray of light starts from A, that's the observer, towards B, which is the remote clock. It arrives at time TB at B, and then is reflected back to the observer at A, where it arrives at T-A. So there's a diagram for it. And what he says is, in accordance with definition, the two clocks synchronize if TB minus TA is equal to T-A minus TB. It's a clever solution to the problem because of the symmetry of it. The effects of distance are cancelled out in the calculation. So it's a clever and good solution. One important condition, though, is that the observer A must be at rest in the coordinate system that's used to define the speed of light as c. It's only if A is at rest in that system is the speed of light c in both directions, and therefore all the calculation works out. You could rearrange the terms in that equation to say that TB, that's the time the remote clock, is half of TA plus T-A. In other words, if the average of those two times equals that time, the clocks are synchronized. Einstein doesn't discuss in detail the practicalities of how this could be done, but the simplest way to do it would be if the clock at B has a reflective face, then if a light, sorry about this, if the clock at B has a reflective face, then if a flash of light is sent from A to B, then reflected back, there will be an image of the position of the hands on the clock at B in the reflection back to A, so A can read what was the time at clock B when the ray arrived there. What's interesting about it is Einstein only discusses the method with both clocks stationary in the same coordinate system, but in fact TB only depends on the position of clock B at the moment when the light flash hits it and is reflected back. It doesn't depend, it's not affected by the state of motion of clock B, so the method works equally well if clock B is moving relative to the coordinate system. The only proviso is that clock A and observer at A must be at rest in the coordinate system. We then move on. There's some bits that cause confusion. Sorry about this. In part one, in section one of the paper, Einstein says, It's essential to have time defined by means of stationary clocks in the stationary system. However, in section 2, he discusses a moving rod, and he says, at the two ends A and B of the moving rod, place clocks which synchronize with the clocks of the stationary system. That's to say, the time corresponds to time in the stationary system. These clocks are therefore synchronous in the stationary system. I said on the previous slide that the synchronized method would work equally well if the observer is trying to synchronize a remote clock which is moving. This statement, to my mind, in Einstein's section 2, shows that Einstein, in fact, accepts that. The key thing is he accepts that it is possible for a moving clock to show the same time as clocks in the stationary system. This is important, and you'll see as things develop, this will come back. Well, we're on definitions. This may seem a trivial one. What is V in his equations? Well, he says in his main analysis, which is section 3, let us in stationary space take two systems of coordinates, and to the origin of one of them, that's small k, let a constant velocity be imparted in the direction of increasing x to the other stationary system. So from that definition, V is the relative velocity of the observer's coordinate systems. In effect, it's the relative velocity of the observers. Another simple question, what is x in his equations? Well, he says if we place x dash equals x minus vt, a point at rest in system small k, that's the moving system, must have a system of values x dash y z, those are stationary system coordinates, which are independent of time. So if x dash is x minus vt, then x is x dash plus vt. So x is the x coordinate in the stationary system of a point which is at rest in the moving system. In other words, the point is moving at velocity v. We'll move on now to more details of his analysis. This paper is famous for its many thought experiments, and this is where we start into the thought experiments. The first one, I've called it, the first bit of the analysis I've called experiment A, because there are differences between this bit and the parts that follow later. So I've called this experiment A to distinguish it from the different ones which follow. This one, we have the two coordinate systems, capital K, which is so-called stationary, and small k, which is moving at velocity v relative to it. And he says, from the origin of system small k, letter A be emitted at time t0 along the x-axis to x dash, and then be reflected back. Now, he gives times, these are times as measured in the moving system, small k, and the equation he gives is half of t0 plus t2, I should say in Greek, tau 0 plus tau 2 equals tau 1. You'll notice that where tau 0 is the time at the start, tau 2 is when the reflected ray returns to the observer at the origin of system small k, and tau 1 is the time when it's reflected back from the remote clock. Note here that he's got that the terms in the equation have subscripts to identify their meanings. This becomes significant later. I'll only show you that if you wrote the same equation without the subscripts to identify the different meanings of the terms, that's what you would get. And you would look at that and say, well, yes, that's true, half times tau plus tau equals tau. It's true, but it's essentially meaningless. I've shown you this. Watch how things happen as we follow his analysis through. So experiment A there's a light flash in the moving system sent to the remote clock and then reflected back to the origin of the moving system. He then, and notice in this one that the light path in both directions are equal. He then looks at the coordinates of the same thing happening in the so-called stationary system, capital K. The thing that's the most immediately obvious point you can see here is that while the light paths were equal in the moving system, in the so-called stationary system, they're unequal. Because as the light heads away from the observer, the moving system is also moving away, so the light has to travel further. On the other hand, when it's reflected back towards a system which is moving in the opposite direction. The logical implications of this are not discussed in his paper, but you can see that if the outgoing light flash arrives at the remote clock in the moving system and in the stationary system simultaneously, then the return flash cannot possibly, the event of it returning to the origin of the moving system cannot be simultaneous. Basically, if those two are simultaneous, then these two cannot be simultaneous. Alternatively, if you assume that point where they both return to the origin of the moving system, that the light flash returned there simultaneously, then they cannot have arrived at the remote clock simultaneously. So the events he's comparing are not actually the same. Einstein doesn't discuss this problem in his paper. If we move on, we're into his calculations now. He bases his calculations, this is the formula we had for the moving system for the light flash outward and returned, and the average of the two at the observer's clock is equal to the time at the remote clock. That's the model he then applies here, but he refers it to the coordinates of the stationary system. Now, remember I said about subscripts in this. There are subscripts in this equation. Notice there are no subscripts in this equation, which leads to problems. So what actually are the meanings of the terms? If we look at it a little more closely, in this set, the coordinates are x dash, y, z, and t. So we can say we've got x dash equals 0, y equals 0, z equals 0, and t equals t. If we then look at this one, at the remote clock, we have x dash equals x dash, y equals 0, z equals 0, and t equals t plus x dash over c minus v. And then we come back to when the light flash returns to the observer, and we have x dash is 0, y is 0, z 0, but t is t plus x dash x dash over c minus v plus x dash over c plus v. I think you can see there is a problem. If you take those at face value, the only logical conclusion would be x dash must be 0. Because if x dash is 0, then we have t equals t, t equals t, t equals t. Completely logical, but true, but utterly meaningless. An analysis based on that is going nowhere. The alternative interpretation must therefore apply, I think, that the terms on the left, x dash, y, z, and t, represent general variables, and the terms on the right, that's these ones, represent particular values of those variables. So they should have subscripts to identify them. So, for example, in this one, it's fairly obvious that this t is the starting time of the experiment, which should be t naught. And secondly, what is this x dash here? Well, it's fairly obvious that that must be the x dash coordinate of the remote clock, which we could call more logically x dash 1. So if we apply the subscripts that I think would make sense of the equation ends up as this. So the particular values that are signified by the terms are identified by 0 and 1. I've also added a's in to signify that this is an equation that's been derived from his thought experiment A, to distinguish it from equations derived from other ones. He now moves on, takes this equation 4, and he has some calculus. He says that if x dash be chosen infinitesimally small, we get these derivatives. Now, before going further, I'll ask the same question. In this, what does tau mean? What is x dash? And what is t? It's fairly obvious that the tau he's talking about is tau 1, that's the time in the moving system when the light flash is reflected from the remote clock. And it's fairly obvious that this x dash here must be what I've called x dash 1, which is the x dash coordinate of the remote clock. But what's t? One thing it's not the t that appears 3 times in this equation, because that t is just the starting time of the experiment, and in fact, shortly afterwards, Einstein sets that to 0. So, get this right now. Yep. So the t that he's referring to could be the time when the light flash reaches the remote clock, or it could be the time taken for its return journey, which is x dash over c plus v, or it could be the average of the times for the outward and return journeys, which is half times x dash over c minus v plus x dash over c plus v. Einstein doesn't say which of these 3 different times is the t in his equation here, but if you look closely at the equation, it looks as though he's actually, where they've been kept separate in the first line, and by the time he gets to equation 7, they've been bundled up together. So it appears, t in this appears to be some mixture of those different timings. Now, from that, he derives experiment 8, which you see there. Notice that he set t at the start of the experiment as 0 and said the origins of the coordinate systems coincide at that time. This is an equation that he relies on heavily in the subsequent analysis. However, if you look at it, you can see it is a false equation. That's a big claim to make. Why do I say that? Well, this equation as written clearly implies that x dash and t are independent variables. However, if you look back at the equation it was derived from, then if t is the time when the light flash reaches the remote clock, t equals x dash over c minus v. If t is the time for the return journey of the flash, it's x dash over c plus v. If it's the average, then it's the average of them. The point, as you can see very clearly here, that t has been set to 0, so t equals x dash. T is a function of x dash. If t is a function of x dash, they are not independent variables, and by implying that they are, this is a false equation. Moving on, having set that equation, he then, remember that previously we said that the light flash went outwards and then was reflected back. he changes that assumption now. He says for a ray emitted at time tau equals 0 in the direction of increasing, get my Greek terminology correct here, it is xi, yeah, xi. That's the x coordinate in the moving system. He says for a ray emitted at time in the moving system in the direction of the x coordinate in the moving system, he gets this formula. And you can see that what I said in the previous slide is correct and accepted. He's accepting that t is a function of x dash. What he hasn't done is explain why he's only considering now the outward flash and ignoring the other possible alternatives. If he'd considered the return flash, he would have come up with the equation x dash over c plus v equals t. If he'd considered the average of the two, he would have come up with that equation. However, he's settled on this, which means he's changed his assumptions halfway through his analysis. We then move on. He calculates c equals c tau. That's the x coordinate in the moving system, the speed of light times the time in the moving coordinate system. He inserts that into this equation, and he gets this equation here, equation 11. He then inserts equation 9 into equation 11, and he gets c, which is the x coordinate in the moving system, is this times x dash in the stationary system. What he doesn't do is, that, to me, it's completely obvious that if this equation is true and this equation is true, then it must also be the case that that equation is true. It simply amounts to dividing by c. Whoops. Oh, this has gone crazy. Simply divide by c and you get time. He could have derived that equation. It's difficult to believe that having worked this out, he wasn't also aware that this must be true. However, he doesn't mention this equation in his following analysis. We then move on to a thought experiment where the light flashes travel in a different direction. So I've called that experiment B. In this, he's considering light rays moving along the y or z axis. That's a diagram of what he proceeds to analyse. So, the moving coordinate system, that's small k, is moving at velocity v. The light flash travels along the y-axis of the moving coordinate system, and therefore in the stationary coordinate system, it must go in a diagonal path. Based on that, he works out those equations 13, 14, and 15. Then he proceeds to combine equations from the two experiments. Now, I would point out to you that, first of all, his justification for this. At the end of experiment A, he says, it is to be noted that instead of the origin of the coordinates, we might have chosen any other point for the origin of the ray, and the equation just obtained is therefore valid for all values of x dash y and z. This is his experiment A. Everything, the observers, the clocks, and the light flashes were all aligned along the x-axis. He's saying the equations obtained are therefore valid for all values. I remember reading that thinking, just a moment, that's a big assertion to swallow. It doesn't present any detailed analysis to justify it. And I'm not sure that it's true. Checking some simple facts shows that in fact it's not true. In experiment A, where everything was on the x-axis, x dash was x minus vt, y, everything was on the x-axis, so y was 0, z was 0. Then in the moving system, c was c tau, and eta was 0, and zeta is 0. In the experiment B, where the light flash is travelling in the y-axis, x dash is 0. Y of the equations I showed you last slide, y is t root c squared minus v squared. Z is 0, c is 0, eta is c tau, and zeta is 0. So you can see that equation, x dash equals x minus vt, is not the same as x dash equals 0. You can see that the equations in experiment A are not the same or as in experiment B, and in fact they're not valid in experiment B. So this big assertion that he wheeled out without any justification isn't in fact true. Despite all this, Einstein then wants to derive the Lorentz equations. He combines equations from the two thought experiments. These are the equations that he uses as a basis, and this is the analysis that he does. So he starts with equation 15 and 16, and he says, well, if x dash is 0, then this equation becomes eta equals act. He can then combine that with this equation to get that. He then changes from this function a, he then rearranges things so it disappears. It becomes a function of phi v and beta, where beta is 1 over root 1 minus v squared over c squared. From this, he gets eta equals phi v times y. He then says that motion along the x-axis cannot affect the lengths in the y-axis direction, therefore eta equals y, therefore phi v equals 1. With phi v equals 1, he inserts that along with this substitution back into equation 8 to get this, and then substituting x dash equals x minus vt, he gets the Lorentz equation for length transformation for time. I've explained some of the flaws and inconsistencies in the equations that he's combining, but some of the things can be illustrated also quite simply. I mentioned earlier there should really be subscripts to identify individual terms. If we go back to these equations and add in the relevant subscripts, you can see what happens. The first equation is from experiment A. Then equation 13 is from experiment B, but this equation is from experiment A. So he's combining the two experiments with light flashes in the different directions that were inconsistent with one another. Then this equation is an experiment B equation, and this equation is an experiment B equation. And the simple problem that you can see once they're actually labelled is x dash in experiment A is not the same as x dash in experiment B. Eta in experiment A is not the same as eta in experiment B, and y in experiment A is not the same as y in experiment B. So he's combining apples and pears, and the fact that there's something wrong can be very simply illustrated by bringing in that equation a couple of slides ago that I showed you, the one that Einstein ignored, but it follows exactly from his analysis. If we combine it with equation 15, x dash equals 0, we get tau equals 0. A digression at this point, the function phi v, there's a major error in the calculation as presented in the English translation. Einstein introduces a third system of coordinates, capital K dash, which relative to moving system K, small k, is moving such that the origin of coordinates of system small k moves with velocity minus v. He then says, on this basis, system capital K and capital K dash are at rest with respect to one another. A point of explanation here. System small k is moving at plus v relative to system capital K, the so-called stationary system. So if system small k is moving at velocity minus v relative to the new system k dash, then k dash must be moving at plus 2v relative to k. It's not at rest relative to one another. On the face of it, it's an absolute whopper of an error, and it makes a nonsense of all of Einstein's subsequent analysis. However, before we rush to blame him for this one, I checked the German text. And this phrase of system K simply isn't there in the original German, in Einstein's original German text. It's been added by Perrott and Jeffrey in the English translation. If we remove it from the text, then this effectively is saying that the origin of k dash is moving at minus v relative to the moving system. And then Einstein's statement is true. So it looks as though that phrase, those three words, were added by the translators in a misguided attempt at clarification. It is concerning that there's a translation error in the most commonly used English translation of Einstein's paper that makes a complete nonsense of his calculations, and it's not been corrected in print since 1923, and it's been repeated in Hawking's 2007-2008 edition. Let's go back now to the combining of equations to get the Lorentz equations in a bit more detail. This is what Einstein did to get the Lorentz equations. He started with equation 8, combined it with 13 to get this equation. He then combined that with equation 15, x dash equals 0 to get eta equals ACT. Then equation 14 gave him that. If you follow through, then he brought back in equation, so equation 8 makes a second appearance. Combining that with a is 1 over beta, he got t equals that, and combining that with equation 2, x dash equals x minus dt, he got the equation that he wanted. So it's quite a complicated selection of equations, and it's interesting that this equation makes two appearances, once with x dash set as 0 and one with x dash not set as 0. That was Einstein's solution. However, it's not the only possible solution. We could select different combinations of equations and see where those lead. We could take equation 8 and 13 and combine them as Einstein did, then combine them with x dash equals 0 as Einstein did, and then combining, as I've just shown you on the screen now, if you combine that with equation 13, you get tau equals AT. Therefore, if you then make these substitutions, you get tau equals t root 1 minus v squared over c squared. In other words, tau equals t over b, which is not the same as that. So we could pick different ones of Einstein's equations, combine them differently, and get a different answer. We're not finished yet. If we combine equations 8 and 9, we get that. If we then combine these substitutions, we get tau equals t over root beta, over beta times 1 plus v over c. So by choosing another selection of Einstein's equations to combine, we've got a third possible answer, and we're not done yet. Start again with equation 8. This time substitute t in equation 8, and we get that equation. Substitute x dash equals 0, and we get tau equals 0. So, by picking different combinations of Einstein's equations, it's possible to get 4 different solutions. There's Einstein's solution plus at least 3 other possibles. So his claim that the Lorentz equations can be deduced as a unique solution to his special theory of relativity fails. Moving on to time dilation. This is how Einstein derives his equation for time dilation. He considers a clock at the coordinates of moving system small k and adjusted to show moving time. What is the rate of this clock viewed from the stationary system? He puts that x equals vt into his transformation equation, and he gets that the moving clock is moving slow by half v squared over c squared. However, firstly, you can see from that his calculation of the clock running slow is based on the Lorentz equation and x equals vt. But remember, either system capital K or system small k could be considered to be the stationary system. Remember, at the beginning of the talk I pointed out that he accepted that it was possible for moving clocks to show stationary time. And in experiment A, which was light flashes along the x-axis, we also had x equals ct. How do we reconcile those? Well, what I think we can do is go back to the actual equations that Einstein derived from his special theory of relativity. If we consider what are the coordinates of the origin of moving system K, in the moving system, the c, eta, and zeta, that's the x, y, and z coordinates of the moving system, are all 0. It's the origin of that system. In the stationary system, x dash is 0, y is 0, and z equals 0. We can then enter those values of variables into the equations that Einstein calculated directly from his special theory of relativity. In experiment A, if we take equation 4 and put in x dash equals 0, we get t equals 0 for the outward flash. For the return flash, we again get t equals 0. For the two-way flash, we again get t equals 0. For his equation 9 based on a one-way flash, we get t equals 0. Equation 10 based on the coordinates of the moving system and a one-way flash, c equals c tau. If c equals 0, tau equals 0. Then go to experiment B, which is light flashes on the y-axis. One-way flash, equation 14, t equals y over root c squared minus v squared. If y equals 0, then t equals 0. If we go to the moving coordinate system, there's eta equals c tau. If eta equals 0, then tau equals 0. So the only conclusion that we can draw from Einstein's equations is that t equals 0. That would reconcile this contradiction of x equals ct and x equals vt. If t is 0, then x is 0 and everything's all right. But what we can see is that Einstein's special theory of relativity calculations tell us nothing at all about how the timekeeping of a clock at the origin of one coordinate system compares with the timekeeping of a clock at the origin of another coordinate system. His special theory of relativity equations do not predict his time dilation equation. His time dilation calculation was based on the Lorentz equation, not special theory of relativity. So, final slide, we come back to the twins paradox, about which so much has been written. The late Al Kelly identified 54 explanations of it by different authors. Einstein himself gave different explanations at different times. I could say a lot more about it, His explanation in his 1905 paper is very speculative with strange jumps of logic, and there's only a tenuous connection between it and his main analysis. There are also some serious translation issues in the English text. However, as I've just shown you, he based the twins paradox on his time dilation calculation, not on his special theory of relativity equations. His time dilation calculation was based on the Lorentz transformation equation. This may be why people have had problems explaining the twins paradox. If it exists, the explanation sits with the Lorentz equations, but in Lorentz's theory there is no twins paradox. If it's possible that the twins paradox doesn't actually exist at all. A heretical question: is the clock paradox actually compatible with the principle of relativity? That's how Einstein defined the principle of relativity. If the laws by which the states of a physical system undergo change, if the operation of a clock is a law by which the state of a physical system undergoes change, then any effect of motion must be symmetrical. Also, the clocks may appear to run slower than one another, but according to the principle of relativity, they cannot actually run slower. It's therefore possible that the principle of relativity specifically rules out the clocks and twins paradox. How about that for a controversial conclusion? Now I'm going to switch off screen sharing. If I can.
I should be able to bring it down, which probably will short circuit that.
Right.
Okay.
So you can see that's fine. I'm back on screen. So conclusions. I looked at Einstein's 1905 paper in an attempt to understand the clock's paradox, but it didn't end up that way. His analysis is superficially simple and clear, but scratch the surface and look below, and you'll find that it's complicated, messy, and full of errors. There's confusion over definitions of terms. Thus, his stationary system's not stationary in the normal sense of the word at all. And either his stationary system or his moving system, either of them could be considered to be stationary by his definition. Speed of light is constant. What is it constant relative to? Well, by his definition, it's constant relative to the so-called stationary system, which is the observer's coordinate system. What is v? V is not the relative velocity of clocks. It's the relative velocity of the coordinate systems. In other words, it's the relative velocity of the observers. What is x? Well, x is the stationary system coordinate of a remote clock which is at rest in the moving system. In other words, a moving remote clock. In his early analysis, Einstein accepted that moving clocks could show stationary time. The Perrott and Jeffrey translation that's been used by generations of students has a major translation error in the middle of the analysis that makes a complete nonsense of Einstein's calculations, and this has been uncorrected in over 100 years, and it's repeated in the 2007 edition edited by Hawking. That's pretty outrageous in a standard university text, but I think it also gives an insight. It shows that English-speaking physicists have not paid enough attention to the details of Einstein's calculations. If they had been following Einstein's calculations in details, they would have spotted it and made the correction. So, summing up, Einstein's calculations are full of errors. He has inconsistent assumptions. He produces incompatible equations and then he combines them. To obtain his transformation equations, he selected the combination that gives the Lorentz equation, but it ignored at least 3 other different possible solutions based on different combinations. His claim that the special relativity calculations lead to the Lorentz equation as a unique solution is not true. On time dilation, his calculations from his special relativity equations only give you that t equals 0, tells you nothing else about the timekeeping of clocks in 2 different coordinate systems. Time dilation he calculates from the Lorentz equations, not special relativity, So if you want an explanation of time dilation's paradox, you must look at the Lorentz equation. But in Lorentz's theory, there is no twin paradox. The idea that a moving clock will actually run slower than a stationary one is incompatible with the principle of relativity. So it can be argued that the idea of a twins paradox is incompatible with Einstein's special theory of relativity. I would say the reputation of his 1905 paper as one of the great papers in science needs to be reappraised. It's full of errors and it does not prove what it claims. Unless an analysis is produced which corrects all of Einstein's errors but results in the same conclusions, the link between the special theory of relativity and the Lorentz equations is broken, and new thinking is needed. If we hold on to the special theory of relativity, we must replace Einstein's calculations, and this may change the transformation equations. If we want to keep the Lorentz transformation equations, then we need an alternative explanation for them to replace Einstein's. Now it's over to you.
Well, goodness me, that was very illuminating, and I've had a look at your paper actually, but someone is trying to enter the studio. We have 10 people, so there's no more room in the green room, unfortunately. However, I'm going to take down your slides, which might give one more space. Yeah. So I found that very illuminating, and it helped actually to look at the details that Alasdair has shown on his website actually, and in the paper, and then going into the equations. Now, if you all have a bit of patience, because Roger, I see you. If you'll permit me a little time, Gary's putting the thumbs up. We'll go through the questions first, because there are quite a number of questions here which I think I'd like to get Alasdair's take on. I think the participants would. And maybe we can make a few observations, and then we can go back to the green room, because the green room was actually full. We now have one extra space available, as I've taken on the slides. But just some brief observations, as I'm permitted now to make these. Obviously, the problem is in the initial clock synchronization, just taking the average of the to and fro times for the light signal seems to be problematic. But I mean, it has been pointed out that the glaring factor C plus or minus V, which appears in the paper, seems to go fly in the face of everything that he's saying. I mean, so much so that that's actually a bit of a no-no for physicists now. If they see that factor, they say, "Oh, you're a crackpot, take it out," Or they may even divide by C and get 1 plus or minus V over C, which is innocuous because you don't see that. Actually, there may be a comment which is related to this, but it occurred to me that all this, and Alasdair's very clear exposition of how he was going about, how Einstein was going about deriving the Einstein's principle from these kinematic considerations, might lead one to the suspicion that he knew what he wanted to get to, namely these transformations, and that he was sort of twisting things around a little, particularly as has been pointed out by Alasdair, that the solution he adopted is actually not unique. It's just one of many. And of course, the other question of translation problems, has been brought out from the German. That problem, which actually subsisted for quite some time, from the German to the English translation. So, perhaps just before spending a little time going through the comments, we may have to spend a few minutes doing that. Now, Alasdair has disappeared because he's probably brought it. No,
I'm still here.
You're still here, but you're.
Yes.
I don't know why your video's not up. I didn't actually remove you. Oh, there you are. You've done it. No, it's somebody else doing it in the background. I have people here like Franklin and Roger who have controls, and they're doing things without my knowledge because they're co-hosts for other meetings. But, okay, it's Roger who did it. Okay, so Alasdair, if you want to make any quick observations on what I said, about maybe he knew what he wanted to get to, the Lorentz transformations, and he was therefore being a bit.
That one in particular The more I puzzled my way through his paper, the more it became obvious to me that he presents it in the traditional way that, oh, I started with these principles and now I'm doing these calculations and look what answer comes out. But that isn't what he did. There are so many twists in the calculations, it's abundantly clear. He knew the answers he wanted at the beginning, and he massaged his let's use a neutral word, massaged and directed his calculations to get the answer he wanted. And the whole array of errors I've pointed out are just the things that happened in the process. He was trying to, it was a force fit of calculations from one theory to another. And once you correct his errors, the two don't line up at all. But he definitely knew the answer he wanted before he started.
Well, that's quite a clear take we will take out of this talk, whether people agree with it or not, because there has been a suspicion in people's minds, certainly in my mind, I think in many others, this was the case. But if we think there's a strong case to be made, well, you've made it very clear, actually. You've given very clear reasons why this may have been so. So let's just see, are there any quick questions that there are so many questions here. There are scores and scores and scores, and as I say, we have a full green room. So let's just try to see, are there any questions here? I know there are a few that I thought we might want to put to you straight away. One guy, by the way, said, well, he'll be making some comments on the recording. So if you look at the recording, you might see a few comments, but it's a bit too late to interact then unless you get onto an individual correspondence. Okay. So, these are just administrative things. Okay. Right. People have been asking about invariance of equations and so on. Dare I say it? I mean, it's pretty turgid, all this stuff. I must confess. But actually, the mathematics, the level of the mathematics, is actually very low. It's just really, high school algebra.
It's second year high school maths.
Yeah, quite so. Because a lot of people say, "Oh, the maths have put me off, and I couldn't do it." But actually, if you just persevere a bit, you'll find that it's not advanced as maybe general relativity might be. Okay. Well, this is for me. A comment came in. If the moderator approves, may I give a link to On the Electrodynamics of Moving Bodies right here? Well, that's the original Einstein paper, which is freely available. You can get that in English. Please put that link in if you haven't done it. We can give it to you. Good. Technically, I don't know what he's saying here. Technically, a given mistaken theory could have consistent logic that follows a faulty premise. Have you anything to say about the two premises as quoted in the 1905 paper, Alasdair? At the very beginning, really, which you talked about briefly.
Yes. He effectively stated them as opening assumptions, as the principles he was going to do his calculations from. All I've done is, okay, if those are your assumptions and you're doing your calculations based on those, I'm going to look at your calculations, and his calculations don't stack up. There's an alternative version of the question we ask could be, well, it is possible to get the right answer from the wrong theory. It doesn't change the fact that the theory is wrong.
Yeah, I think he seemed to extend the ways he expressed those propositions, which seemed fairly innocuous to me anyway, because, I mean, they're almost like the Newtonian or Galilean relativity, which he's extending to optics and electrodynamics. But if you didn't have an ether as a reference frame, you could claim that. Just as if you didn't have air, for example, you would have Newton's first law would be absolutely true. Not because you have friction and things like that. The second proposition, insofar as he quotes it, merely says, actually, if you read it, and I think you pointed this out as well, that the speed of the ray is independent of the speed of the source, which is quite true. But that's true of all all radiation. It's true of any wave, motion, sound and air, water waves. But what he does is, because of the principle of relativity, he says everything is equal. So the observer is exactly equal to the source. Observer motion is equal to source motion. It's only the relative speed that's important. So therefore, he extends it to saying that the speed of light is independent of the speed of the observer, and that is untrue.
But that would, he says that the speed of light is c relative to the quote stationary system unquote, and the stationary system has to be the system that the observer is stationary in. Therefore, implicit in his definition is that the speed of light is c relative to the observer. I should say, you could, if you wanted me to summarize my conclusions in one sentence, it would be the basic proposition of Einstein's paper is, if you take those principles and them only, you can deduce from them the Lorentz transformation equations. What I've shown is that that statement's not true. His attempt to derive the Lorentz transformation equations from those principles fails, and therefore you're back to square one. You can have either the Lorentz equations, or you can have those principles, or somebody's got to come up with a much cleverer and better new analysis. But no matter how you come at it, Einstein's 1905 attempt is a failure.
By the way, we posted some references on, and one man here, person said, oh, he got a blockage thing. If I may just be so bold to say, I got that as well. I think maybe the systems are not recognizing your website. So I just said, proceed anyway. And, it didn't wreck my system. So I don't know if you're aware of that, Alasdair. But
I don't know. No.
But anyway, I got into your site and it was excellent. There was so much information there. So I'd encourage anybody to do that. Okay, let's move on. David Bauer, I know, has comments, but he's left now. So we may have to come back to that. Now, let me see now. I mentioned earlier, by the way, in relation to my statement, that we had one or two people who are very mainstream. We have one man actually who does like a lot of comments, but he's not here today. So we may come back. That's Andrew. I think Alan Kelly made a positive statement about the moderatorship or something, which is appreciated. I don't think there's any comment yet. There are a few comments here. Let me see. We get through them quickly so we can get to the chat in a moment now with the people in the green room. Okay. George James Dukas. Let's see what to say. Yeah. Well, it's the same sort of thing as we've been saying. The creators of SR, made the assumption that space-time is real and LT operates in this domain. So, that, for example, in the time coordinate, t dash, you not only have t, but you have the x coming in. And this gives. There's been some discussion in the emails actually with regard to Minkowski's, four-dimensional analysis and so on. Why was there? Was the maximum possible? Yeah. Okay. Some of these we were just had discussions between ourselves. I'll not bother with them because we've sort of discussed this. Yeah, okay. Okay. God, the comments are still coming in, so I have to keep moving. Yeah, just again, I mean, you're all frightened with the maths, but if you do persevere, it is actually quite comprehensible. And Alasdair, very right on that. And a lot of the equations you give actually are just the equations of the 1905 paper, and then you're analysing it.
They're all from it.
Yeah. All the tau and the T and all that thing. Yeah. Okay. Okay, we'll get that. But by the way, I'm going through this very quickly because we could easily spend the next 3/4 of an hour just going through the questions and we'd have no time for chat. So if I'm missing anything, please come back and put question for Alasdair, because I could easily be missing anything as just conversations between participants. What evidence is there? So let's see. Well, so the question was asked about this. I sort of put this comment in. And I wonder what your take. Do you agree, disagree, or I just said, well, actually, it was Voigt maybe who put in the first form of equations with a parameter epsilon, which if it's one and so on, we get the Lorentz. And then it was Poincaré actually in 1904, I think, who christened them as Lorentz transformations.
Yes.
But this bit was my own idea. Just what you say about the requirement for the the wave equations and Maxwell's equations to be covariant. Well, these are the equations which would do that.
Yeah. I'm aware that what are known as the Lorentz equations, different versions of them were produced by various people in that in that period. What I'm saying here is that you have the Lorentz equations and you've explanations for them proposed by several people, including Einstein in 1905. I'm saying whatever the validity is of anybody else's explanation, Einstein's equation doesn't work. Einstein's explanation is false. It's full of errors. His explanation for those equations has to be dropped. You can then go and look for, if you want to keep those equations, you've got to look for a different explanation for them. Einstein's 1905 explanation is false.
Well, I use the word osios, which just means, without any consequence, because my own analysis, anyway, for what it's worth, is that if you use total derivatives in the electromagnetic equations rather than partial derivatives, which somebody actually pointed out here earlier on about the total derivative, well, then the Galilean transformations work perfectly. And I noted actually that Alf O'Rahilly in this big tome, he actually used the word independently. He said they're osios as well. So I'm not the only one. We came upon that term independently. Now, okay. Just talking about invariance of the equations. Okay, we're getting near the end of the question, so we can very shortly go to the green room. And you pointed out these 54 possible explanations that Kelly listed, and that would perhaps indicate, we have discussed this before, that would perhaps indicate that they're just accepting a dogma, as you pointed out, perhaps incorrectly formed, and then trying to rationalize why it is the case. And they're all contradictory.
I think that's exactly what's happening.
Okay. Point well made. Okay. Now, what's he saying? They're talking about the variable speed of light. Let's go on. Okay. Harry has pointed out that others have pointed out maths errors, and I know Roger has. So we'll come to you in a second, Roger. We're just coming to the end of the. You want to come in. Invariance of Lorentz equation is meaningless because there are no. So what he says is. I've got the wrong one, is it? Yeah. That's Harry says the invariance of Lorentz equations in SR is meaningless because there are no physically meaningful solutions to SR. Yeah, well, that's saying the same thing in another way, isn't it? Somewhat, Alasdair. Like the contradiction of the clock paradox that A has to be slower than B, but B has to be slower than A.
The thing I did want to bring out was we've spent a lot of time agonizing over the twin paradox, but because of all Einstein's mathematical analysis is so full of mistakes, I think it probably, the twins paradox probably doesn't need it to. If it does exist, it's got to be explained by a different theory from Einstein's one. But the different theories from Einstein's don't actually predict a twins paradox. So we may have all spent a lot of time debating something that doesn't exist, was only generated by his mathematical errors.
Yeah, quite interesting. So you can spend a lot of time trying to save something which is actually based on falsehood.
Yes.
Alasdair, the paper, I think, which is generally available on the web, and you mentioned the translation, did you? Did it have that error in it?
Yes.
Which you said was subsequently taken out.
No, it wasn't something.
But that's the one you use anyway. You get that English language.
The one I made a big. There are other translation problems at other points, but there wasn't time today to go to all them. The one I made the play about today is just a blatant error in one. It's not Einstein's error. It's not an error that exists in other translations. It's just unfortunate that it exists in the most widely used English translation, and I just think there are no excuses for that, especially when Stephen Hawking was bringing out a new edition.
Yeah, you mentioned that. Good point. Now, Alasdair, I'm looking at the thing, and I see Nick Percival has had his hand risen, so I'm going to bring Nick up. Good day to you, Nick, and the floor is all yours to address Alasdair and make any points you wish.
Alasdair, I am so glad that you came today. I absolutely loved that presentation. I'd give you a standing ovation, but then my head would snap off. I'm connected. I've certainly seen, there are printed thousands of presentations, but I like the fact that you went back to the very basics. And I think this is one of the easiest to understand. And the math is simple if people can take time to go over it. It may be difficult to absorb it on the fly. I'll just make one point. I wrote a paper that was published by the Institute of Physics that I think of as being a conceptual explanation of what you talked about. So if people had trouble with the math, let me just put it up at least into the green room chat to let them know. So I love the fact that you just went back to the basics, and I think you discovered the essential flaws. Basically, Lorentz had it right, at least based on the empirical facts up to that time. He wrote that relativity theory in the late 1800s. And that is what Einstein really took in body and tried to reshape it. So yes, indeed, he knew what the answers were, because Lorentz had already come up with length compression and clock retardation. Even there, Einstein screwed it up even more by calling it time dilation. So that makes it quite clear, and I think there's nothing wrong with the relativity principle as stated, but I think Einstein's interpretation was that phenomena, including contraction and time dilation, he had to take out the notion of there being a preferred frame. So no one could mention a preferred frame and be consistent with his interpretation. But if you interpret the relativity principle as saying, okay, if it's velocity with respect to some physical entity, then everyone agrees with that, and everyone writes their equation that way. There's no conflict with the relativity. It just needs a less restrictive interpretation of Einstein. So, and I think that the 1905 paper really has influenced a whole lot of what's being taught on college, even up to this day. I know when I was at Harvard, they had two Nobel Prize winners on their faculty, and two more were getting Nobel Prize. Yet, they accepted this 1905
Wait.
and never mentioned that there were disagreements, that there were, that was a total surprise to me. And I came to Harvard quite naive and thought, well, the one thing I can trust is that everything that these learned physicists, these pillars of physics, said was absolutely correct.
Yeah, we could probably all echo that to a certain extent, Nick.
Yes, and so I followed the same path you did. I said, how can this twin paradox thing be accepted? I don't understand it. Let me look into it, and followed a similar path to you. And I think the reason why there has been such a long thing is not that dissidents are focused on it. It's that relativists don't seem to be able to grasp the dissident problem that's presented. So what has to be presented over and over again, and of the 54 explanations, 53 of them agree with the dissidents that Einstein's solution that it's due to his time dilation is wrong and can't be accepted. So that 53 of them have sort of accepted that it was a paradox as written. It's kind of interesting. So again, Alasdair, I thought that was a wonderful presentation that really got to the basics, and I think if anyone has an open mind, I think all humans believe that their current belief system is cast in stone, so anything that comes against it, the natural reaction is to say, okay, it's wrong, let me see how it can be, I can explain that it's wrong. But anyone who comes to that with an open mind should be able to see these fundamental errors that you pointed out so clearly. And thank you for doing the math. Those math points were really, really telling. One other quick thing is, I thank you for mentioning John H. Field of CERN, who I've talked to a lot, and his problems with special relativity. Thank you.
Well, thank you very much, Nick. And you know, as you probably are aware, in fact, you guys were in touch with each other before I did. Nick introduced us, Alasdair, so that was great. So you know all about Nick. He's been working for many, many years, 60 years.
And oh, by the way, nice beard.
we all look like aged men. I think you have the longest one, Alasdair.
The longer the beard, the more credibility one has. That's what I'm saying. I'm working on more credibility.
Okay, so anything quick you want to say about in response to Nick, or I suppose you're generally in agreement with that, Alasdair, before I bring it down?
Just a brief observation that's around it. The mystery of why Einstein's paper was so accepted once I started to see all the errors. And people get into very complicated conspiracy theories and so on. And I don't go for that stuff. I think what happened was, at the time he brought it out, he came up with an answer that was the answer everybody wanted. They knew ether theory was in trouble, but they knew they liked the Lorentz equations. Einstein said, oh, I've got this great I've done these calculations, and actually, you can use relativity theory, which they're liking better, and you can get the Lorentz equations. What's not to like? And they basically thought that's fine. He gave them the answer they wanted, and he gave them lots of esoteric conundrums and questions to debate and do further research on, which is exactly what any researcher wants. So basically, I think he gave them what they wanted at the time, and because it was so much what they wanted, nobody checked his maths.
Another reason why it was so well accepted was he stole from the correct theory, so that if you do your experiments in the true stationary frame of reference, then you get the right answer. So that's why they say, gee, Einstein's theory has been confirmed by experiment to 9 decimal points, but they forgot that it also confirmed the Lorentz.
Of course, a lot of that came later with the general relativity, with the eclipse expedition in 1919.
Yes,
It
yes.
became
Sorry, I'm going on a wee bit too much, but generally speaking, physicists work with the Lorentz equations, not with Einstein's theory. They make the assumption that the two are one and the same. And all I'm pointing out today is, oh no, they're not.
Right. Thank you very much, Nick. Well, just putting you in the hot seat for a second, just I don't know if you're able to answer this very quick question, but haben Sie etwas zu versollen? He's asking what German word was used for stationary. Do you remember in the German?
Oh, see, I didn't look at that. I'm sorry about that.
I've forgotten. I remember looking.
It's actually, though, my complaint on stationary is his definition. It's not a linguistic problem. It's a conceptual one. He shouldn't have called it stationary when the whole basis of his theory is there's no such thing as stationary. That's the problem on the stationary system. The translation problems are more to, there are other, I would have to take a quarter of an hour, which I'm not going to. There are various other important things that are about language problems.
Yeah.
But I think that one's not a language problem, it's a conceptual one.
Well, I'm sort of rather convinced that the sort of errors that you've been pointing out today and related ones are more fundamental, actually, than the misconception and mistranslation ones. Now, I'm not sure if Roger would agree with that, but they're all difficult.
Well, I definitely believe that. I definitely believe that.
You agree with that? Yeah.
Oh, yes.
Okay. We've come to the same conclusion then. Okay, now, there's not much time left, so I don't think I'll get everybody in the green room through today because we have 10 people. But anybody, Denny has his hand up. He's just anticipated me. So you're very welcome today, Dr. Dennis P. Allen, Denny.
Yeah, this is the cover page of a paper, Tolerable Asymmetry, that Ron Hatch, the last of the great GPS people, was writing at the time he died. He asked me to help him out with it a little bit by looking for errors. And intolerable asymmetry, and because symmetry is everywhere in Einstein's special theory. And he's saying, no, it should be asymmetry, tolerable, which is tolerable. It's not, as most special relativity people would say, is wrong. No, it's tolerable. Scripture, yeah. Ron in his paper quotes scripture on the cover page. Yeah. And he believed that the symmetry was the real problem with special and general relativity, and so he was creating a asymmetrical theory, which he used to, as the last of the great GPS people, he used to get tremendous accuracy out of the GPS. When it first started out, it would tell you if you were on the road about where you had to turn, but if there were two right turns right next to each other, then it couldn't tell you which one to take. But after Ron Hatch got to it, the accuracy was phenomenal. It was unbelievable. And the day he died, writing this paper, Tolerable Asymmetry, The day he died, he maintained that when the physicists say that special and general relativity are why the GPS system works, liars.
What your view is on Einstein said actually he wasn't aware of the Michelson-Morley experiment when he first wrote the paper, and then maybe that was contradicted. You know, do you think that was in his consciousness at all to explain that?
I think
So do I. Yeah. So do I,
yes.
to be honest.
There's his once you get under this properly dig into his paper. I think as I said at the beginning, I think his stroke of genius was to spot the problems that were occurring in physics and what a very clever solution would be, and basically go with relativity on one side to get rid of the ether problems, but go with the Lorentz equations because they were giving useful results. And he basically tried to back one of those into the other. And as I've tried to show today, you look at his sums, he failed. They don't marry up, on at least by his logic.
All right. Now, unfortunately, the time is clicking away very rapidly, notwithstanding any paradoxes. But so what we have is Roger, I think, has asked for the floor again, and I'll perhaps give him that just for a moment or two. But just, I want to see if anybody else. We have one more possibility. So I think it's Vladimir and Cornelius. I don't think we have time for both of you. I'll bring you up, but could you be very, very brief? Because Vladimir, thanks for coming in, but if you could be very, very brief, the time is caught up on us. So Vladimir, you yourself will be talking to us on your own.
Okay. Very brief. Thank you so much for great presentation. Never I thought so detailed analysis of principles. It's not an issue of translation from German to English. It's a principle issue. I cannot get so named stationary system. Stationary against what? I have no clue about it. That's why I have a very short question. What will change in your analysis if instead of stationary system, we will put absolute frame of reference in conjunction with ether, with the medium I will talk about, with something real. Even, by the way, even in general relativity, there is so named perfect fluid. All these general relativity Friedman equations, they are with Friedman perfect fluid. Ether, perfect fluid, medium, it does matter. But there is something stationary, and you can define your stationary system like an absolute frame of reference, and then proceed with your analysis. Did you do such analysis?
No, I have to confess, these are very interesting questions, and I don't know the answer to all of them. I've focused on a very narrow point, which is, did Einstein manage to show that his theory predicts the Lorentz equations? And I found that the answer to that was no. And I think that, what I do think is, if people can get that clear in their heads, it opens the door to cleverer people than me to come up with theories to replace what Einstein's done. All I've done is try and knock his one. Well, I think showed that his one collapsed. I've not tried to knock it out. Shown that his collapses, so it needs to be replaced. I'm not clever enough to know what the replacement is.
So very well.
This replacement will be, go please to absolute frame of reference. Next time I will refer to this frame system, and then you will be updated your analysis against the real medium of our world. Thank you so much.
Well, we look forward to hearing that exposition from you, Vladimir. And we know in the not too distant future you will be giving us those talks at some depth. So thanks very much for raising that point. Because one or two people have raised the matter of stationary relative to what and so on. But quite honestly, it was Cornelius who did that. I think the point is well taken. I'm going to give you a moment or two, Alasdair, that's why I was cutting things off, to complete your say, and just to summarize very, very briefly, and then I'll come in and close the meeting officially. Okay.
I don't think.
Sure.
But yeah, I've said what my conclusions are. The essential conclusion is Einstein set out to show that the Lorentz equations could be reconciled with his special theory of relativity as he set it out in 1905. He failed, and therefore people need to go back to it and either come up with a new analysis to completely replace his 1905 paper and be lucky and reconcile them, or else they've got to choose. Are they backing special relativity, in which case the Lorentz equations go, or are they backing the Lorentz equations, in which case special relativity goes? Now, there's a whole pile of, if you accept that that's where we are, there's lots of interesting research and discussions to be had. But first of all, we've got to look in the face the conclusion that Einstein's 1905 paper is not what it is claimed to be. It needs to be kicked. It needs to be knocked out of the fundamentals of physics and replaced by something better.
Well, that's an extremely important message to give, whether everybody agrees with it or not. And Harry has said there are numerous other papers that agree with what has been said today. So if I may, I just bring it down now and close the meeting officially. I'm delighted we had Alasdair today, and if I may say so, you have people who have studied this, but maybe are not every day working in the area, the full-time physics professors. Perhaps sometimes that can confuse the public. They can say, well, if these guys who are working in CERN and working in astrophysics and so on say that everything is hunky-dory and we don't need to review it, why should I listen to Alasdair Beal, or why should I listen to Ian Cowan, or why should I listen to Harry Rick or anybody else? Well, I would make a plea that perhaps we have the ability to look at this in a fresh way. And certainly Alasdair has gone into very, very great detail, which I think I might have lost patience with. I have had a look at the 1905 paper some years ago, and I did lose a bit of patience with it. But I came to sort of an instinctive feel that it was going about things in the wrong way. And Alasdair has given us very, very good reasons to think that he perhaps massaged the results a bit. And it's been a very, very clear presentation. The slides have been very, very clear. Now, I know he's gone to a considerable amount of trouble to produce this paper in the first place, and I suppose that's given the basis to it. But to add to that and to explain to us, in fairly clear language with very good visual aids, the CNPS is indebted very, very much to Alasdair for that. I'd like to thank him very, very much, and I hope we'll see more of him.